Mike Strickland. Mike, please share your screen. You have to be co-host. Okay.
Yep.
Masoud, can you help? Can you help? Okay, here you go. Okay, now it should work. Okay. Yeah, Bottomonium suppression in the quark-gluon plasma. The stage is yours.
Great. First, thanks to the organizers for inviting me for this workshop. I'm hoping that, through further communication with these two ends of the world, that we'll make further progress in quark-gluon plasma physics. So what I'm going to talk today about is about two papers that were with the Munich group, Nora Brambilla, Miguel Escobedo, who gave a talk yesterday, myself, Antonio Vairo, a student named Peter Vandergrind, and Johannes Weber, who's now in Berlin. And there is one paper which is already, I believe, published in JHAP, and in the end, I'll show you some forthcoming predictions. And now, good. So quarkonium suppression in particular has had a long history, right? So going back and even to the late 80s, people started to predict that if you were to take a bound state of a heavy quark and an antiquark and put it into the quark-gluon plasma, that you would find that above a certain temperature that it would start to melt. It would dissociate into free quark and antiquarks propagating through the plasma. And the original understanding of this was due to Debye screening in the plasma. As we increase the temperature, the interaction becomes more short range, and then the states fall apart. But what we've come to understand in the last 10 years is, while this is in fact happening, another effect that's occurring is that if you drop this quarkonium state into the medium, of course, it's being buffeted all the time by, or hit all the time by in-medium gluons. And this turns out to induce a very large in-medium spectral width. And by large, I mean on the order of 50 to 100 MeV for like the upsilon 1s state. And that large number means that it's actually undergoing decays on a time scale of the quark-gluon plasma lifetime. So it's decaying inside of the plasma with at a much larger rate than it would in the vacuum. And so to understand this in completeness, you have to model both of these effects. And we now know that this weaker color binding here is associated with modifications of the real part of the potential. This is sort of related to the singlet free energy that you can see over here. The black is the real part of the potential at T is equal to 0. And then these various lines are when we start increasing the temperature. And as we can see from this little picture, if we had a bound state that might be living up here in this potential, by the time we get to this very high temperature, it will be unbound. But as I said, there's these large spectral widths that we also have to contend with. Right, so how do we observe these upsilon states? These upsilon states are observed in the di lepton channel in general. This is data from LECB, and they use the di muon channel. So this is di muon invariant mass, and this is essentially number of hits here. And as we can see, there's some background, which is going down smoothly, but standing on top of this background is the upsilon 1s, the upsilon 2s, and the upsilon 3s, which are very nicely resolved by this LECB experiment. So this data was collected in proton-proton collisions, and we can see that the resolution is very high, and we have, we can resolve these states, and they have some intrinsic width, which is, I don't want to get into where that comes from, but anyway, they have some width. Now, if we imagine we could place these bottomonium or quarkonium states in general in the quark-gluon plasma, what we would find is that as we jacked up the temperature, their widths would get smaller, their masses might shift by a tiny amount, but the primary thing is that their widths are getting super large, and eventually you won't be able to identify a 3s state in the plasma at all. And if you keep jacking up the temperature and don't take this number as gospel, you would then disassociate the upsilon 1s completely. Now, we can see this effect in experimental data with our naked eye. That's one of the things that I like about this observable in particular. Here on the left is again some PP data. This time, instead of from LECB, it's from CMS. And you can see again, super high resolution in the case of the PP collisions. In this case, they've normalized to the background. And again, we see the 1s, 2s, and 3s peaks standing out here. And if we look at the right plot, this is what the data collected by CMS in a lead-lead collision. That's the blue line that's hiding down here. And then superimposed on top of this is the PP data now on top of the background, since the background is still in this plot. And as we can see, so this is PP data, but it's been scaled up, right? What does that mean? We have to multiply by the, on average number of PP or nucleon-nucleon scatterings that occurred in our nuclear collision, and that will tell us our expectation, essentially, that nothing happened, no quark-gluon plasma or anything interesting that wasn't already accounted for by PP physics. That would be the red line here. And we define an observable, which is called RAA, which is the suppression of the state, which is basically the ratio of the peak here to peak here. It's a little bit more complicated than that, but that's conceptually all that it is. Now, of course, we see this very strong suppression in the quark-gluon plasma case, and it's not just CMS that's reporting this, it's also ELISE and ATLAS, so there's a lot of data being collected on this observable. Of course, in heavy ions, we have to be a little bit careful, and we have to run the control test. And in this case, the control test is proton on lead. And as we can see here, the left plot again shows the PP scaled result, now a prediction for P lead, and the blue shows the actual measurement. And as we can see, there is some suppression of the excited states and also the ground states due to just cold nuclear matter effects, essentially, or co-movers, it depends. But this is a sort of our control case. In a min-biased PA collision, we do not expect quark-gluon plasma formation. So this is the level of modification we just get from modifications of the nuclear parton distribution functions and co-movers and stuff. And then you should compare and contrast that to the right, which is the same result I showed you on the previous slide, which is the lead-lead result. And here we can see that it's dramatically more suppression than you would get in the P-lead. Now, this is an important point to make in the beginning, because in the old days of charmonium, there was some confusion because the order of magnitude of these two effects could be the same. And so it left people with a giant question mark of whether or not what they were seeing was truly quark-gluon plasma formation or just some cold nuclear matter effect. Now, I'm going to focus on bottomonium, not primarily for that reason, primarily for the theoretical reason, and that is simply that their masses are super big. And by having this high energy scale, we can now exploit things like heavy quark effective theory, where as the mass goes to infinity, essentially the scale separations open up and allow us to do things systematically. The other thing, as I just mentioned, is that these cold nuclear matter effects decrease with increasing quark mass. Conceptually, you can understand this as they're giant small bowling balls flying through a pool of very small ping pong balls. They're not going to be very much affected by the light degrees of freedom. They will be affected, otherwise they would they wouldn't be suppressed at all. But they're not going to have significant cold nuclear matter effects, especially because the time scale is very short for this to occur. And because their masses are so large, you cannot produce them thermally, right? So the probability to produce a thermal pair, a bottomonium pair, is about e to the minus 10. So you only produce them in the initial hard collisions, and their numbers are completely conserved after that. So they provide a nice probe of the plasma. They're produced at very early times. On the order, for upsilon, for example, the formation time is on the order of 0.2 Fermi over C. So these guys can now provide us a history of what was happening in the plasma, presumably. The other reason that bottomonium is nice to focus on is that both closed and open bottom production is quite rare in RIC and LHC energy heavy ion collisions. You're lucky to get one or two pairs, right? Two pairs is even rare. So as a result, the probability for having something like statistical regeneration of bottomonium is much smaller than for charm quarks, where these production cross sections, at least at LHC energies, can start to become large. And then we have to worry about the fact that a charmonium state might have broken up due to some plasma effect, but it might pair back up with some open state that's just flying around in the plasma. So as a result of the fact that we'd have less regeneration, we have less model uncertainty. So those are the three 4 big points rather that I want to start with for why to consider Bottomonium. Now, in general, this would also apply for Charmonia, but again, let's focus on Bottomonium. The conceptual problem is the following one. We're going to have some incoming quantum mechanical state, which can be described as a linear superposition of some ground state, 1s, 2s, and if it has a fixed angular momentum, let's say L is equal to 0, these will all be L is equal to 0 states, but it will be a linear combination of a quantum mechanical superposition. And again, as we learned from quantum mechanics class, if we want to get the probability to find that this state is actually an upsilon 1s, it's the modulus squared of this coefficient and so on. And now we want to take that quantum mechanical linear superposition, we want to fly it through the quark-gluon plasma, have some quantum dynamics here, and on the outside, we're going to get a linear combination now with different coefficients. And of course, the probability now to find the upsilon in the final state is related to A prime modulus squared. And if we want to know the relative probability, we just take the modulus A prime squared over modulus A squared. And that will tell us essentially the survival probability of this quantum mechanical state. You can also think of this in the language of the density matrix. We have some incoming density matrix, which has some probabilities for each of the eigenstates. And then after it propagates through the quark-gluon plasma, it's going to have some different probabilities. And the ratio of these two, again, would give us the survival probability. So as I said, we can think of it as a kind of brick because these things are formed early. They're not outside, they're formed somewhere in the plasma, and then they propagate through the plasma and then they escape. And the bound states during their traversal of the plasma can break up for these two reasons I mentioned earlier, and potentially reform due to in-medium transitions, right? So you could have an upsilon 1s state, which is a singlet, for example, and then it can get hit by an in-medium gluon, and then it can become a octet 1p state. And that would look like naively to be dissociation of the 1s because it's no longer in the 1s quantum state. However, at a later time, another in-medium gluon can come along, or the thing can actually release an in-medium gluon, right? And then it can de-excite and go back down to the ground state. So we need to take into account this gluon absorption and emission, and also the fact that these states are not only in the singlet state, but can also be in octet states, which are unbound, but they can be unbound for a short amount of time and then come back to bound states. So we have to be a little bit careful here. So the other complicating factor when you first approach this problem is that the quantum evolution that's here in this block turns out to be non-unitary in general. And before I get to the more formal way of understanding why this evolution is non-unitary, I first wanted to run you through a sort of heuristic way of understanding this, and that's by looking at just noisy quantum mechanics. So we're going to imagine they're heavy quark bound states. We can describe them with a kind of non-relativistic picture. I'll try to provide some justification for this later. They have an in-medium potential, as we've learned, that has a real and imaginary part. So where does this imaginary part come from? So let's look at a system where I just have some non-relativistic bound state with a local potential V, and I introduce now some time-dependent noise function, which is acting on both the quark and the anti-quark, but it has the same correlation, this two things. It's just a 2-point noise source. The noise is averaged to 0, and it has a specific correlation function, which I'm going to call D. It's uncorrelated in time, so each time step is not correlated. And now we can imagine what would happen if we tried to shoot our state through such a potential. Now, of course, on an event-by-event basis, you would generate new noise at every time step, and this will influence the dynamics of the system. But what we would want to do is, instead of looking at a single instance of the noise, we want to average over all of the noise. And the average over all the noise is averaging over the noise of the environment. So we have these light degrees of freedom in the quark-gluon plasma. They're providing fluctuations to the hard particles. And now we want to average over all those fluctuations and essentially do the path interval, if you like. So we're going to now average over the medium fluctuations in the path interval. Now, to do this in this simple heuristic way, what you have to do is just take the time evolution operator, expand it out to second order, and then because this noise correlation function has a delta function here, there's a factor of 1 over the time interval that pops out. And that means that these noise terms that you introduced into the Hamiltonian in the beginning, you can't throw them out because each of these terms is going to be on the order of 1 over delta t. And so you get some updated evolution, which now it takes into account this noise that's coming from the medium, essentially. And if you average over all possible noise configurations, well, the first part, which was with the bare Hamiltonian, it doesn't care. But the second part, which came from the second order term in the time evolution operator, well, it's still around and it's got an I sitting here and it's proportional to these correlation functions of the noise. And you can rewrite it in terms of this correlation function I showed you on the previous slide. And you can see that once you put in this noise and then average over the noise field, you get an effective evolution, which looks like something that has a normal kinetic energy term of potential, and then also some imaginary part that's related to the noise. And my way of understanding this is that the imaginary part emerges through interference of the wave function with itself when we sum over the environmental noise. So we have to imagine doing this, shot by shot through the environment, and then quantum mechanically adding all that together. So, but that's not the way we understand it these days, but it's a way that you can quickly get to the fact that if you do this separation where you have some medium that provides some perturbation on your probes, you can then almost immediately see that you're going to end up, if this is really fluctuating, you're going to end up with some imaginary part to the potential down here. Now, in some sense, this is not new for old school nuclear physicists. There's this. There are imaginary parts of scattering cross sections related to absorption and things like this in the past. So how can we understand this more formally? And that starts from what we call an open quantum system framework, in which we split our entire system into some probe, which is going to be our heavy quarkonium state, and the medium, which is the light quarks and gluons that comprise the quark-gluon plasma. And then we can formally decompose the total Hamiltonian into a probe part, a medium part, and then of course there's going to be some interactions between the probe and the medium. And then depending on how you treat this, you could use perturbation theory or some other technique. That's where the magic comes in, is how you treat the interactions. What I'm going to show you today is using potential non-relativistic QCD to treat this term, essentially. And what we want to know in practice is if we have the density matrix for just this part of the subsystem, which is the probe part, how does it evolve in time? Because remember, going back to this picture, if we know how the density matrix evolves in time, then we can calculate this survival probability. Now, if we were dealing with the total density matrix of the system, I keep clicking in the wrong place, then we could write down the total density matrix. This would be a thermal density matrix. But in general, the time evolution of the total density matrix, we know that from quantum mechanics class. There's just a commutator of the total Hamiltonian with the density matrix. However, if we trace out these medium degrees of freedom here, formally written as trace over medium of the total density matrix, what is the evolution equation? And in general, this procedure generates an equation that looks like this with an extra term, which is called a master equation in general. And these master equations need not be Markovian, but in some limits they can become Markovian. And one of those limits in which they become Markovian turns out to be one that's applicable to Bottomonium physics and the quark-gluon plasma. And the result is something called the Lindblad equation that's shown on the bottom of the slide. So why do we end up with this Markovian Lindblad equation from maybe this more general master equation? Well, it has to do with the separation of timescales. So in general, for an open quantum system, you have three relevant timescales. One is the medium relaxation time, which tells us how fast the system, at least the light degrees of freedom, react to being perturbed and then relaxing back to equilibrium. In general, we know that this is going to be on the order of 1 over the temperature. So if the temperature is higher, this is going to relax much faster. There's also going to be an intrinsic probe time scale, which is related to the internal spacing of the levels in the probe. If it was a hydrogen atom, right, for example, you would be jumping from the 1s to the 1p state. There's a spacing there. This is the spacing, the time scale associated with those quantum jumps, if you like. And then there's also something called the probe relaxation time, which is how much how quickly the momentum of the probe itself will relax. And in the limit that this the relaxation time for the probe and the intrinsic probe time scales are much greater than the medium relaxation time, and this is the only assumption you need, then you land in this Lindblad equation. And as you can see, the first term looks like what we would expect from normal quantum mechanics. We have some commutator, but now it's just between the probe part of the Hamiltonian and the probe part, which we call the reduced density matrix. But then there are these extra two terms, which have some new operators, which are called Lindblad or collapse or jump operators, depending on the literature you're reading. And what you find in general from such form of an evolution equation is that, well, it's nice because it's trace preserving. So if the trace of the reduced density matrix is 1, it will be 1 at the end of the evolution. That means we're keeping track of everything, at least in the space of the reduced density matrix. It's completely positive, so you'll never get negative probabilities and weird stuff like that. And then finally, in general, it's a non-unitary evolution, which I'll try to step you through in the next slides. But before doing that, let's jump back to these new operators that appear. These operators, I'm going to call them the jump operators from now, because that aligns with my intuition. And what they're doing is they're connecting these internal states. So these CNs are representing internal transitions within the quartonium states. Now, how can we understand that this is the correct limit just looking at Bottomonium physics? So I just want to remind you of some of the scales in Bottomonium physics, right? The bottom mass is on the order of 5 JeV, the upsilon mass itself is on the order of 10. And the system is basically non-relativistic. V is much less than 1. If you compute the relative velocity of the Q and the Q bar, it's on the order of 0.1. And then by simply cracking open the PDG and looking at the spectrum of the states, you can very quickly convince yourself there's a hierarchy of scales where the binding energy, which is basically the level spacing, is on the order of mv squared. And then this fine structure that's sitting here is on the order of mv4. So just by looking at the spectrum, you can almost immediately see, well, it's probably a non-realistic bound state. Looks like a hydrogen atom, probably very close to a hydrogen. As a proof of principle, what I show you in this table on the right is just what if you plug in a Cornell potential, and just try to solve it with the bottom quark mass in place and some spin-spin mixing, right? I had to include that. And here are the experimental data for all the upsilon states, and here are the ones that we made predictions for, at least from this potential model that we used in the paper. And here's the relative errors. So hopefully the last column convinces you that at least in vacuum, these things are extremely well described by just a non-relativistic model. You can improve it by doing further expansions in V and so on. So it's a nice systematically improvable theory. And even the first pass at it, you get pretty close to the answer. Now, formally, how we're going to derive our results is by starting from QCD, but we can't solve QCD exactly because it's a hard problem, as everyone knows. But in this case, because the mass of the quark is much greater than both lambda QCD and T, we can simply integrate out the scale m, and that can be done perturbatively, again, because m is super large compared to both of these scales. And if you do that systematically, you will end up with what's called the non-relativistic QCD Lagrangian that has various bits. I won't go through the detail, but this was sort of groundbreaking work by Caswell and Lepage and Bogwin, Bratton, and Lepage back in the mid-90s, where we can now make this really systematic. Now, just for the students in the audience, these Ds and Es, these are not external fields. These are essentially the internal chromoelectric fields and chromodielectric field inside of hadrons. And I won't go through the details, but there's a sort of explicit, sort of power counting and separation of scales that you can exploit in this case. Now, it turns out that you can go one step further than integrating out this mass, which is the largest scale, you can then go and integrate the next scale, which is the soft scale, which is m times this presumably small parameter v. And that turns out to be related to the inverse size of the states. And if you do that, effectively what happens is some four quark interactions with some highly complicated propagators, and imagine any Feynman diagram you like here on the left. They get mapped to sort of point-like vertices in this potential non-relativistic QCD theory times some Wilson coefficients, which are determined for matching, which become the potentials. And as I said, there's the kind of explicit power counting where you can do all of this systematically. And when you do it, you find out that the resulting degrees of freedom for this now potential non-relativistic QCD theory are singlet and octet states. I'll show you the Lagrangian on the next slide. It allows you to obtain manifestly gauge invariant results. It's easier to connect to lattice, and it's systematic. The Lagrangian itself looks like this when the dust settles, at least as the order I've shown it to you. Here's some pure gauge part. And then, as I said, we're going to have a Lagrangian written in terms of singlet fields that interact through a singlet potential, and octet fields that interact through an octet potential, with those two given below. This is an attractive potential, and this is a repulsive. In addition to this normal evolution, which would, for the singlet and the octet, we have some interaction terms, which can be derived systematically in this theory. They come out to just be sort of dielectric transitions, if you like. And that in this way, we can understand that a singlet, by absorbing or emitting a gluon, can actually transit into an octet, or we could also have octet-octet transitions if the gluon is appropriately put in the color space. Now, based on this Lagrangian, once you have it, this becomes your new starting point. You don't have to do QCD anymore. You can just use this Lagrangian. And then you can start doing calculations. For example, in the Schwinger-Keldysh formalism, you might want to know what's the self-energy of the singlets and the octets in this system. And the reason that's relevant is because we want to know the rates for these transitions in general, and those come from cuts of graphs like this. And so these graphs that I show here, they're actually what you need to compute to get those Lindblad collapse or jump operators. But you can do it straight from this Lagrangian. So to summarize, what we're going to do in practice is we start with QCD, we do a perturbative matching. We can then get this non-relativistic QCD Lagrangian. We can then further integrate out the inverse size scale, and then we can get down to this very simple Lagrangian that looks like just singlet and octet degrees of freedom. And so with this picture, we can now understand why this was the relevant choice of scales to pick. So we have the temperature, as I said, we have the mass, which is much bigger than the temperature. We have the bound state size, which is much, the inverse bound state size is much bigger than the temperature. And we also have potentially, because there's a temperature around, we also have a Debye mass. There can be screening in the plasma, as I mentioned earlier in the talk. And then there's the scale of the binding energy, which you can think of as that level spacing from the graphs before. And as I alluded to before, if you look at the medium relaxation time scale, what you'll find is that's just simply 1/T. Intuitively, this intrinsic probe time scale is going to be parametrically 1 over the binding energy. Again, this is the level spacing. And this one is less intuitive, but it's related to 1 over the self energy. And you can actually derive what this time scale is parametrically. And what that results in the end is, if you take the standard assumption from non-relativistic, from potential non-relativistic QCD, that translates it to exactly this condition that we said was necessary to obtain a Lindblad equation. And just to focus on this for a second, so this means that the temperature is going to be much bigger than the binding energy. The Debye mass is going to be much bigger than the binding energy. But the temperature and the Debye mass, we're not going to make any assumption about their ordering, because as we know, for phenomenologically relevant temperatures, these two can be on the same order, or perhaps even inverted compared to our perturbative expectations. And then finally is the bound state size, which we always assume that this guy is super small for a Bottomonium state. in vacuum at least, it's 0.2 Fermi, right? They are super small. All right, so with that, we can land with this Lindblad equation. But I promised you earlier that I was going to tell you how do you get back to this kind of imaginary part of the potential picture from such a complicated looking evolution equation for the density matrix. And the way that proceeds is by first knowing something physical, right? So these collapse operators Cn here, they encode in the end the total decay widths to different internal states in this case, right? So for the guy to jump to say a p wave state and not be in the upsilon 1s anymore, that might be one of these ends here. And for each of those, the width for those transitions is simply given by Cn dagger Cn. And if we sum over all of the possible transitions, that will give us the total decay width into any of these possible outgoing states that the system might want to go in. And so then if we, with that understanding, if we go and look at this equation, we can see that what's hiding here is a sum over Cn dagger. That's nothing but this, the total decay width. And we can now group these two red terms together into a blue term, which I'm going to call the H effective evolution. And here with a normal Hermitian evolution operator for the probe now gets modified by this total in medium width. So this is just encoding the fact that it can decay into all possible states, be it bound or unbound, right? So they're all included here in gamma. And then once we make this translation, we can write our evolution equation as a sort of evolution with the non-unitary Hamiltonian plus some jump terms. And it turns out this first part gives you, as Miguel Escobedo discussed yesterday, gives you a very good approximation to the result. And in fact, in the large NC limit, it gives you the exact result. If NC is not large, then you need to take into account this extra term, and I'll discuss that next. But before we do that, let me show you what the form of all the operators in this equation will take. So we proceed in stages. So the first thing we're going to do is take the density matrix and decompose it into singlet and octet blocks. And then later we're going to decompose it into angular momentum blocks. But let's stop at the first decomposition. So we go here, there's a singlet and octet block. It's represented as simply a 2x2 matrix in this case. And by doing this calculation of the self-energies in pNRQCD, you can derive explicit expressions for these jump operators. And there's 6 of them, and they cover all possible transitions, singlet to octet, octet to singlet, octet to octet. So that's shown here. So you might throw in a singlet S-wave state. It will evolve for some time, and then it will jump potentially through absorption of a gluon up to an octet state that it has L equal to 1 by the selection rules. And then it can keep doing this dance and jumping around in all possible ways that obey the selection rules, which also includes jumping back, right? So that's all included in these jump operators here. They have some algebraic structure, which is just transitioning between the 1, 0 and 0, 1 states, but they also have a coefficient over here. Some of it comes from color factors, but there's a fundamental number called kappa that pops out here. And that kappa is in red on the bottom of this slide. It's related to a time-ordered correlator of chromoelectric fields, and in this case, the real part of this. And it's kind of related to it is directly related to the momentum diffusion of a single heavy quark in the quark-gluon plasma. And so it's a little bit surprising at first that it pops up here in the bound state problem, but it does. And this quantity then governs the rate of jumping, essentially. So kappa, in this case, it'll tell you the rate of jumping. If kappa is 0, you're not going to jump. You're going to stay in whatever state you began with and just evolve with the non-unitary part of the effective Hamiltonian. In addition to these jump operators, what you find when you do the calculation is that there's also a modification of the real part of the potential, and that comes with another coefficient, which is called gamma. It's a fundamental transport coefficient, if you like. And again, it's a 2x2 matrix because we've decomposed into singlet and octet space. And this turns out to be related to the exact same time-ordered chromoelectric correlator, but now it's just the imaginary part. So these two go hand in hand. And gamma is encoding the modification to the real part of the potential, and kappa, as it turns out, is going to encode the modification of the imaginary part of the potential. If we calculate the total decay width, we're going to find that it's proportional to kappa, and this comes in with an I, as you'll remember in the evolution. So we have now evolution with this non-unitary Hamiltonian, and then these jump operators, which are listed here. Now, of course, we have to pick some values of kappa and gamma to use. The nice thing about these two quantities, as I said, there was some interest, in particular in the bottom one, in the context of open heavy flavor. So people started looking early on in how to measure this guy. And you can do it on the lattice. So here's some results that were reported in this paper in 2007, which show the scaled coefficient kappa as a function of T over TC. The lattice data are these lines here. And then there's a next to leading order perturbative or pRNQCD result, which is here. And then there's a blue, which is a fit, where they fit some coefficient in order to better reproduce the lattice data. So what we're going to use in all our phenomenology is essentially the blue band. And then we'll vary from the top of the blue band to the bottom of the blue band in order to assess our uncertainty related to this transport coefficient kappa. Gamma, which is the shift of the real part of the potential, less is known about that. Recent results suggest that it may be, in fact, very close to zero, but past measurements have found it to be quite large. And so out of abundance of caution, what we've done is just varied gamma over the range of the lattice data that was available to us when we wrote the paper. I would say as a function of time, gamma seems to be shifting closer to zero, but let's wait for the lattice people to comment on that. So now that we have this organization, how would we go about solving these equations, right? The density matrix is a matrix. So far, we only did the decomposition in color space. We could also do the decomposition in angular momentum space, and then maybe put on an angular momentum cutoff, let's call it L max, on the basis that we use. And then we'll find that this matrix that we have to solve here is as L max plus 1 squared size. And then if we wanted to describe the wave functions that are underlying this density matrix, we're also going to need to solve something numerically on some lattice with some lattice of maybe n points. And then we'll see that this density matrix size is like n squared L squared. And of course, in any computational thing, you eventually want to take n and L max to infinity. And you'll quickly find that it's very hard to solve this equation because it's one, it won't fit onto your computer even, and two, the matrix size becomes so large that you'll just have to wait until you die to get the result. So this computation becomes very challenging if you want to just directly attack the matrix value density matrix. So our strategy was different, right? So usually if we have some problem with a high degree of dimensionality, you might want to consider some sort of Monte Carlo or stochastic approach. And we didn't invent this. People in the atomic physics community invented this, where they had atomic oscillators, right, coupled to some thermal system known as their lab, and they needed to understand how these things evolved in time. And so luckily we were able to benefit from that literature. And one of the things that they invented in the last 10 years was something called the quantum trajectory algorithm. And just to step you through it, what we do in practice is we can just take this first blue term and we can start the state in a given angular momentum and color state. We then evolve it with this non-unitary Hamiltonian evolution. During this time, because it's non-unitary, the norm of the wave function drops. At some point, it's going to drop below a threshold, which we're going to generate randomly what that threshold is, as it turns out. And then at that point in time, it will jump. And there's a set of rules that you can derive from once you know these jump operators, the probability for making jump or no jump, or jump up or jump down, right? Once it's jumped to the target state, we reset the norm of the wave function. We start evolving again, but now with a new Hamiltonian evolution, which is appropriate for L is equal to 1 in an octet state. And then once again, we wait for the norm to drop below some threshold, and then we trigger a jump again. It might jump up here, it might jump over there, it might jump back down. And that's controlled by some probabilities encoded in these jump operators. And so that's how we're going to do this in practice. So we have we just have some Hamiltonian evolution, be it non-unitary, interspersed by stochastic jumps. Now, the important thing here is that in between jumps, we're always in a well-defined angular momentum and color state. And therefore, by rotational symmetry, we can reduce that problem down to a 1D Schrodinger equation, right? We just have to include the LL+1 term in the Hamiltonian, and then make sure we're using the correct singlet or octet potential when we're evolving the wave function. So this is a great advantage because we no longer have to solve some n squared problem. We have to solve an n, and we can now solve the full 3-dimensional quantum evolution using an effectively 1-dimensional real-time solution. Now, when it jumps, we just simply change the quantum numbers of the state, and then we evolve with the H effective.
Mike, you have to finish at some point. Sorry.
Yeah, what time is it? Sorry, I don't have the time on my
You're
Zoom.
1 minute over the time, but that's okay, because if you need some extra.
Oh, I need a lot of
5
extra time,
minutes.
but I'll just show some quick results without, because mostly I want to introduce the formalism, and then I'll skip over some slides. That's fine. Thanks. I was expecting a warning.
I'm sorry. I was also how to say Masoud gave me the warning, so I give you the warning.
Okay, good. Thanks. All right. So what we need to do in practice is we're going to have to shoot a bunch of states through the quark-gluon plasma. So what we're going to do is then what we use is a 3D viscous hydrocode called anisotropic hydrodynamics. We're going to shoot our states through. We're going to record the temperature along each of these trajectories, and then solve this real-time 3D Schrodinger equation with complex potential and jumps. And then we average over lots of quantum trajectories for each physical trajectory. And then we also, in order to get out the, compared to experiment, we have to average over these physical trajectories as well. Now, once the evolution is done for an individual trajectory, we can extract the survival probability. As I said in the beginning, it's simply the quantum mechanical overlap of our basis states with the final wave function scaled by the same in the initial state. Oops. I'll skip over the feed down, but suffice to say that the story's not over. Once you escape the quark-gluon plasma, there can be excited state feed down that you have to take into account. And so in my last -2 minutes, I'll quickly flash some results and then go to the conclusions and ask for questions. So here's predictions for RAA. Again, this is the suppression of the state. So if it's 1, it looks like PP. It's less than 1, you had fewer states than you expected to see. And the experimental data are collected here for the 1s and the 2s states. On the left shows varying the transport coefficient kappa. On the right shows varying this transport coefficient gamma. And as we can see, at least within our theoretical uncertainties, we're pretty consistent with the data. And this holds true also for these double ratios. So if you take the ratio of 2s to 1s, there, a nice thing is that the dependence on kappa almost completely vanishes, and you only have dependence on this, the modification of the real part of the potential. This offers some hope that we can, in the future, pin down gamma by comparing to this observable. With the new stuff, we can also make predictions of RAA as a function of PT, double ratios as a function of PT. If you're interested in this, go back and look at the slides because I'm out of time. And finally, the other thing that we can do is look at flow. And for this, you need a lot of physical trajectories, but with this quantum trajectories algorithm, it's doable given enough machines at your disposal. Now, for the flow, we don't really expect Bottomonium to flow like a light degree of freedom. At least I don't. Again, it's like a billiard ball in a pool of ping pong balls. And that seems to be borne out by the data. The lower left hand shows a comparison with the extracted Bottomonium flow with admittedly big error bars, but at least it's consistent with 0. Same thing was found by CMS, and it's nowhere near the magnitude of what you see for the J side. So with this new open quantum systems framework, we can now make rather precise predictions, at least in the sense that we don't have large model uncertainties or statistical uncertainties in our results. We can do that for the 1s, we can do that for the 2s and the 3s, both as a function of centrality, and we can also do that now as a function of transverse momentum. And sorry for having to go through the second half so quickly, but I lost track of time. All right, so what I wanted to try to get across to you today is that in the last 10 years, there's been a lot of progress using this open quantum system approach. When we sort of began, we knew that there was this imaginary part of the potential, but the physics underlying it was a little bit unclear. And then how you connect that imaginary part of the potential to real world singlet and octet states and transitions there between that 10 years ago was roughly unknown. And it was largely due to the Munich group, and in particular, Miguel Escobedo did amazing work on this front. And what I tried to show you today was the sort of phenomenological predictions that come out of this. And I wanted to emphasize in my last statement that what we've done now is the first full 3D quantum and non-abelian treatment with this open quantum systems approach. Now, other people have tried different things using 1D or only having abelian theories. This is the first time that all the pieces have been put together. And fundamentally, the only two things that we need to know are some transport coefficients called kappa and gamma from the lattice. So it allows us to tie directly into lattice measurements. And with that, I'll end and apologize for running over time.
Thank you, Mike. Thank you very much. I have to apologize for not giving you a warning in time, but I think everybody enjoyed it. Huh? What?
We should make Zoom apologize, because whenever we go into full screen mode, my clock gets blocked and I don't see the clock.
I always switch on my screen 5 minutes before the time, but this time I actually forgot. Sorry, I was so fascinated by your Lindblad equation that I somehow lost track. But let's have some questions. I think, Masoud, do you want to ask your question?
Sure. Yeah. My question was that I guess this is a stupid question to people that do this stuff, but this question was that why 1s has less events than 2s and 2s has less event than 3s, and why these large angular momentum states are more suppressed.
Well, the large angular momentum states typically, from this plot, as you can see, they have a lower binding energy. So even if you go back to the original Matsui Satz picture, these guys, because they have a lower binding energy, they will get dissociated first. So anything that has a lower binding energy here will get dissociated. These guys are, the guy 3s, for example, is almost near the threshold. And then you can also look at these excited states, they have lower binding energy, right? Mm-hmm. That's the first way to understand it. Now, in our modern way of understanding, it's not really the binding energy scaling, it's the width scaling, if you like. And the same thing happens for the excited states. You find that there's an ordering. The ground state width is smaller than the excited state width, which is yet smaller than this guy. And so there's a ranking also of the in medium decay widths, depending on where you are in the spectrum.
Thank you.
And that has to do with the size of the states in the end. These are bigger. And because you have this imaginary part of the potential, essentially the bigger states experience parts where the imaginary part of the potential is bigger. And so you get a larger width.
Does this answer the question, Masoud?
Yes, thank you.
Okay. Chris has a question. Okay.
Hi, Mike. First of all, thanks for a very nice talk, very clear. So you mentioned at the beginning the sort of dual role of Debye screening and collisional broadening in producing upsilon suppression. So what I was wondering was, you didn't have a lot of time to talk about it, of course, for the double ratio specifically, but I was wondering, does one expect to find sort of a path length dependence if one, again, there's obvious statistical challenges here, but if one studied the double ratios as a function azimuth, differentially an azimuthal angle? Is there something that could be learned by seeing some kind of, you know, elliptic path length dependence in mid-central collisions or something?
So you want to look at like something like V2 2s over V2 1s or something like that?
Yeah, except it's not, it wouldn't be a momentum space anisotropy.
Yeah.
It'd be an anisotropy in the double ratio itself. So basically you'd have more suppression coming out. You'd have more suppression in plane than out of plane, I think is.
Mm-hmm. Yeah, and it would be interesting to look at. I imagine the variation will be small and similar to what we found for V2, right?
Right.
But it can be done. Yeah.
Okay. Yeah. Thanks.
Thanks for the idea.
Yeah. Any further question? Actually, maybe I can ask one. When you write down your non-unitary time evolution, somehow I had the feeling that you're just adding the Hermitian conjugate. Actually, no, it was further. Yeah, here, there. Sorry, down there or up there. Exactly. Isn't that just the Hermitian conjugate, or is rho probe not an Hermitian operator?
Rho is Hermitian. Yeah. So this is just you know, it's like the commutator, but we can't do commutator, right? Because this thing is
yeah. But isn't this then just the Hermitian conjugate of the first term, or am I?
Yeah, you could write it that way.
So then the sum is Hermitian basically, and
yeah,
unitary, and only the jumps they change.
No. This thing will have because, well, you can imagine because H is well, this is trace preserving, let's say. And,
yeah. Okay.
But if you were imagine evolving, because H is not is not Hermitian. If you evolve with this guy, the norm will not be preserved. Right.
Mm-hmm. Okay. It was more like a technical question.
You will preserve unitarity of the you will preserve the trace of the density.
Yeah.
Will be preserved.
Yeah. Okay. Good. I think we exhausted everybody,
Okay.
more or less. But yeah, let's thank Mike and also all the other speakers of this first session again. And we will resume. I think, should we resume at 4 o'clock, Masood, or do we have a few extra minutes? What is your suggestion? 5 minutes enough for a break? I guess so, huh? So we resume at 4 o'clock.
I don't know. We can have more. I don't have a problem, but